Most of us think about light as a one-way street. A lamp shines, the light bounces off the objects in the room, and that reflection enters our eyes so we can see them. When you turn off the lamp, the room goes black because there's nothing left to bounce. But that's only true for the light our human eyes are built to process. If you turn off the lights and switch on the thermal camera, the darkness disappears. You are actively glowing bright yellow and orange. You aren't reflecting anything. Your body is generating its own light. You constantly radiate about 100 watts of energy in the form of infrared light, a wavelength that sits just outside the visible spectrum, generated entirely by your body heat. Which raises an interesting question. If biological heat makes humans glow, what about everything else? Does a ceramic coffee mug emit light? What about a cold rock sitting in the dirt? To figure out exactly how matter emits light, physicists use a theoretical concept called a black body. This is an idealized, perfectly opaque object that absorbs all light that hits it. Because it doesn't reflect anything, any light coming off a black body is generated purely by its own internal temperature. What that model tells us is that every single physical object with a temperature above absolute zero is doing exactly what your body is doing. The glow is a universal release of thermal energy happening inside every piece of matter in existence. This chart shows the relationship between temperature and light, mapped out by a rule called Wien's displacement law. It tells us that as an object gets hotter, the peak of the light it emits moves towards shorter, more energetic wavelengths. At roughly 300 Kelvin, standard room temperature, the curve peaks entirely in the infrared zone. This is why you, the coffee mug, and the rock all glow invisibly. Watch what happens to the curve when we apply heat. By the time an object reaches about 800 Kelvin, the peak shifts to the left, and the very edge of the emission spills over into the visible light spectrum. This threshold is called the Draper point, where objects begin to glow a dull, faint red. You see this exact math play out in a blacksmith's forge or an industrial foundry. When solid steel hits those temperatures, it stops looking like gray metal and starts radiating its own visible red-hot light. If you keep pushing the temperature higher, the curve sweeps right through the orange wavelengths. By the time you reach 6,000 Kelvin, the object is emitting massive amounts of light across the visible spectrum, peaking in a blinding yellow-white. That 6,000 Kelvin yellow-white peak happens to be the exact emission profile of our sun. The color of a glowing object is actually a precise mathematical thermometer. By simply looking at the wavelength of light something emits, you are reading its exact internal temperature. In the late 19th century, physicists tried to use classical math to calculate exactly how much energy these hot objects should emit, but their equations produced an outcome that made no sense. According to the classical rules of physics at the time, as an object got hotter, it shouldn't just produce a neat bell curve of light. The math predicted it would emit an infinite amount of high-frequency ultraviolet energy. If those classical equations were actually true, simply opening a heated oven in your kitchen would blast you with a lethal infinite wave of radiation. Obviously, that doesn't happen. The old math was broken. The problem baffled the scientific community until 1900, when a physicist named Max Planck decided to try a completely different mathematical approach. To make the equations fit actual colors in the real world, Planck had to drop the assumption that light was a smooth, continuous wave. Instead, he proposed that electromagnetic energy could only be emitted in tiny, indivisible packets. He called these distinct packets quanta. Because higher frequency light requires larger energy packets to produce, the probability of an object emitting them drops drastically. This quantization naturally caps the high-frequency light, curving the math back down into the exact finite bell curve, perfectly matching a blacksmith's forge or a yellow star. If light can only exist in these discrete packets, it means the physical world isn't a continuous slide. It's built on individual, countable steps. This single correction for a heat emission graph eventually forced us to redefine every law governing the subatomic world, creating the field of quantum mechanics. Today, Planck's black-body equations are one of the most powerful tools in astronomy. We can measure the extreme environments of deep space without ever leaving Earth, just by catching the light that travels to us. When we point our telescopes at a star glowing a deep, dull red, the math tells us it has a relatively cool surface temperature. But when we find a star blazing in bright blue-white, we know we are looking at something massively hotter, burning furiously through its fuel. We have even used this same universal thermometer to measure the leftovers from the very beginning of the universe. This map shows the cosmic microwave background, a faint field of radiation filling all observable space. We find it glowing at a freezing 2.7 Kelvin. This perfectly matches the distribution predicted by Planck's law, the most accurate black body spectrum ever recorded in nature. This cold glow is actually the first light from the birth of the universe, cooling and stretching as space expanded over billions of years. It is the fading thermal signature of the Big Bang, obeying the exact same physics that makes your own skin glow in the dark.